right, so today I'll be presenting automation for kind of getting a bounding box to outline a polygon of an object, so a kind of segmentation task. We'll kind of dive into a little bit more of some details in a little bit and talk about different types of proposals that have been done and methods to kind of tackle this problem. Before we begin, I'd like to just kind of review a little bit of the different automation suites that we've gone over. So we've done one for OCR previously. We've also done an instance classification type of automation as well. Previously, we worked on video predictions. And today we're going to look into, like I mentioned previously, going from a bounding box to a polygon segmentation. That's something that we would like to automate for various reasons, which we'll be talking about in a little bit. But that is kind of what we'll be looking at today. This is a kind of general outline for what we'll be looking into. I'll start with an introduction to SuperAnnotate, kind of dive into what we kind of do and how we got started. We'll then talk about the motivation for why we would want to do a bounding box to polygon prediction. I'll share some state-of-the-art methods that have been developed in the couple of previous years. Then we might do a little bit of a demo slash like a coding workshop. And at the end, we'll have some opportunity for question and answers. Great. So just to give a little bit of context to our company and our history, the company was founded in 2018 by two brothers, Tigran and Vahan. They were studying machine learning and computer vision. And Vahan came up with a super pixel algorithm, which made annotating data, especially segmentation, a lot quicker. And that kind of, caught wind of the academic community. And so there was many people interested. In the bottom here, we could see a bunch of our advisors who were very interested in this project. Professor Trevor Darrell, Professor Peter Abil, and also Gary Bradsky, who was the founder of OpenCV. He kind of pushed the brothers to begin found the company SuperAnnotate, so that we could, provide this type of technology to other people. We've raised about $20 million, which has been great for us to expand our team and to be able to bring this to more customers. And we're also very proud of the fact that we're ranked, the top ranked in G2, which is a platform which kind of takes into account, a lot of customer reviews. So this is a sign that the people that we work with are very, very proud with the service that we provide. Diving into the types of services that we have here at SuperAnnotate, on the left-hand side, we can see the data ops platform. So this includes the software that we've developed. We have the ability to integrate via our Python SDK into your own machine learning pipelines and workflows. We have the ability to do robust quality assurance, project management, as well as data management. And we have a bunch of tools that allow you to also automate many of the annotation workflows or data ingestion or output workflows as well. Another part of the services that we offer are our data ops services. So this is more of a workforce management type service where we've gone out and we've vetted many companies, and we've selected a select few, which we think are providing very high quality service. So we work with those teams, and they provide annotators so that they can, using our platform, annotate data for customers and clients, depending on the different types of tasks. And we also have a machine learning ops service, which allows you to leverage solutions engineers to kind of help you integrate our API or our SDK and kind of provide that useful technical support during your projects. Diving in a little deeper into the data operations platform. So this is the editor view that you would use to annotate or label your data. There's a lot of different ways to kind of look into the annotation, so you can kind of provide a curation. Once your annotators have finished annotating the data, they can send it forward to another stage so that you can do some quality assurance on the data. Once that is also done, you can send it further into another stage. And in this way, you can kind of separate different stages of your data as it goes through, coming in as a raw input and being finally outputted as a very high quality annotations. As mentioned previously, our data ops services is there to help you with scaling up. So usually small teams, when they have small amounts of data, it's not a big deal to annotate the data yourself. But as the amount of data that you're dealing with increases, and you don't want your specific engineers to be dealing with the tiresome and tedious process of manual annotation, you can use our services to kind of provide that layer of work for you. And so there's many options to kind of work with us. And yeah, if you're interested in that, you can talk to us about this afterwards. And then also just touching up again on the machine learning ops service, we have the ability to work and give you some consultation around your project, determine the most optimal project structure for you, help you write any conversion scripts that might be needed in case you need different outputs of output formats for your data. And then just kind of also providing an extra layer of technical support for you depending on your needs. Okay, so we're gonna start going into the actual bounding box to Polygon segmentation portion. We'll start off with the motivation of why we want to do something like this. So the first thing that it helps us do is it semi-automates obviously the segmentation of objects that we have. So usually when you're working with segmentation tasks, going around the specific object very tightly, it takes a decent amount of time. It could take anywhere from 30 seconds to over a minute, depending on the object that you're trying to annotate and the complexity of the geometry. So this is something that if we could kind of automate or semi-automate in a sense, it would improve our efficiency and reduce our time for this task. So yeah, this is a great way to reduce the time. And we know that the less time that you spend in this part of the workflow, the less costs will be accrued at the end of your project. So these are, I think, some pretty good motivations to look into and research this type of work. And so the final thing that it also does, it allows us to provide high quality data that could be used as an input to train your models, deploy your services that you're working on, that rely upon segmentation of objects and images. We'll talk about some state-of-the-art methods that have been developed over the past couple of years. We'll begin with Polygon RNN. I'll dive into a little bit more of some specifics and details in a little bit, but this one is kind of like the baseline for these types of jobs. It's RNN stands for recurrent neural network, so we'll talk about how that plays a role into that model. Then after that, we had the evolution of Polygon RNN++, which kind of takes the base of Polygon RNN, modifies it in a few ways, and increases the efficiency and reduces the time compared to its predecessor. We'll also look at Deep Extreme Cut, also known as Dexter. This was an interesting way to tackle the problem. As we'll see, most of the solutions from the previous years, they relied on a bounding box that needed to be placed over the object of interest. A Deep Extreme Cut uses key points to kind of demarcate where you would want to have the segmentation taking place. So we'll look at that as well. And then finally, we have Curve GCN, which stands for, it's a convolutional neural network that's also, I would say it's for graphs. So it's a graph convolutional neural network, and it kind of does something different than the previous methods. And it's, I think currently, or at the time of its inception, it was one of the best methods around for this type of work. Okay, we'll begin with Polygon RNN. So this is a pretty simple concept. You draw a bounding box around the object of interest that you would like to segment. And then the neural network itself will predict the vertices around that object where it thinks it should be. Now, because this uses a recurrent neural network and also a convolutional neural network, the data itself gets downsampled. So the resolution of your output suffers kind of greatly with this method. So that's one of the things that they look to improve in future iterations. But initially, this was a pretty good method to use. You also had the ability to correct any vertex that you saw that was incorrectly placed. So this kind of put the human into the loop here as part of the process for this type of instance segmentation. This process was pretty cool because it actually sped up the annotation process by a factor of 4.7 across all classes in the Cityscapes dataset, which is kind of the de facto dataset that they use for measuring performance in segmentation. It also got a 78.4% agreement in IOU score with the original ground truth, which is pretty good for a semi-automatic workflow. Based on that initial research of Polygon RNN, the researchers decided to kind of improve on that initial model, and they came up with Polygon RNN++. So in this model, they designed a new convolutional neural network encoder architecture. So initially, this convolutional neural network extracts features from your image. In this case, they wanted to make sure that the downsampling wasn't too bad, so that you could still have a decently high resolution output. So that was the reason for designing a new CNN encoder. They also decided to change up the way that they did the training. So instead of doing their usual training with, I think it was MSE, so mean squared errors, they started using reinforcement learning. And reinforcement learning kind of allows you to feed back your predictions into the training itself. And that kind of helped a little bit on performance. And then they wanted to make sure that the resolution of the output polygon that you produce is also of satisfactory use. So they use the graph neural network in the last stage of the process to kind of increase or readjust the resolution for the polygons. And this was a pretty good technique because it requires 50% fewer clicks compared to the predecessor, which is Polygon RNN. Next up, we have the deep extreme cut, also known as Dexter. So as I mentioned previously, this was an interesting use case here where they stopped using bounding boxes as the signal for the neural network input. And they instead focused on using key points. The idea here is that you would select the most extreme 4 key points that you could find. So you would have one at the top, one at the bottom, one at the left, and one at the right. And with those 4 clicks, the neural network could then create its own bounding box and also then segment inside of that area. The average extreme point method was actually 7.2 seconds compared to the 34.5 seconds when we were using bounding boxes to actually annotate. And the reason that happened was when you're drawing a bounding box, you're kind of going around the object, but then after you set the initial bounding box, there might be some leeway in the area. So you have to readjust the bounding box a few times to get it precisely where you would want it to annotate. With this 4-point click method, it was easier to just click on the surface or the boundaries of where you thought the object is, and then the bounding box would automatically be drawn around it. So yeah, this also reduced the lag time between interaction or whenever you're clicking on the points and when the output of the model is presented. So this was also one of the main advantages of using this method. And finally, we're gonna dive into a little bit of curve GCN. So as I mentioned, this was utilizing a graph convolutional network. And the graph convolutional network was kind of used to tackle the problem of the low resolution output that they were getting because of the downsampling. It also allows the ability, so previous methods had a recursive architecture, which means that every vertex was predicted in sequential order. So you would have the first vertex, and then from there you would get the second one, from there you would get the third, and so on. So that sequential process was a bit time consuming. And also when you would readjust one of the vertices, all the other vertices would have to be kind of recalculated in a sense because of the recurrent architecture. So here they tried to avoid the sequential prediction process, and they kind of made it a regression problem. And by doing that, they were able to make sure that all the predictions were done at once. So there was no dependency on the previous vertex in order to have the next one. And the main gist here was that they would kind of create a circular node graph kind of around the object. And then through iterations, they would kind of close in on the actual object of interest on each step. And this was actually a lot better performant than previous methods. It actually outperformed Polygon RNN++ by an order of magnitude. It was running at about 29.3 milliseconds, which is very quickly for these types of methods. And then, like I mentioned previously, if you were to readjust one of the vertices here, you would not affect the rest of the predictions because this isn't a recurrent structure; it's a regressive structure. The only other two vertices that would have to be recalculated would be the ones that are directly next to the vertex that you adjusted. So this has been a quick review about the different types of methods that have been used recently. I'll pass it over now to Vahag so he could show us a little bit of what we've been talking about.
Hello, everybody. So we will talk about how these methods actually work in practice. We will actually see a live demo of them working, especially the Dexter method, which seems to be was one of the best methods, one that optimizes both the cost of time spent and computational resources and accuracy. We will see how it actually works on practice on our platform. We will see that we will also have a live coding session for a second kind of an approach on how you can do these annotations and kind of compromise for or solve some of the negative aspects of the annotation. So let me just start sharing my screen. Right, and hello, can you tell me if everything is fine? Cool. So as you can see, this is the Dexter's official page, and they claim that with just 4 clicks, they achieve 91.5 and 94.4 kind of IOUs on items, on instances of this Pascal VOC dataset. And we have reproduced the results, it is true. And we have also managed to retrain one model for a subset of the COCO dataset. And it again works perfectly well, and we reproduce these findings of their accuracies of the method. And so the most intuitive way of trying to annotate these things is actually trying to speed up the annotation is to have this Dexter method working in the background, letting the annotator annotate 4 points, and then a polygon will be drawn, and then if something is wrong, the annotator will have to correct the polygon. Okay, sounds great, and let's see how it works in practice. We have here, and my session was expired, that's fine. We have here a subset of the COCO dataset. I don't know why this doesn't change the okay, anyway, we have a subset. This is an image. We want to annotate the dog, let's say. And for that, we again put the most extreme points. We find the most extreme points, the topmost, leftmost, rightmost. We have this all for, and then we see that the tool automatically annotated all the rest of the points in the polygon, all the rest of the points on the dog anyway. But this is a fairly good prediction. It conforms with our prediction of having 91% of intersection over union. But as you can see, there are some crop issues. Like here, it predicted a straight line where there's obviously not a straight line, and I'm in the QA mode. I should move away from that. Sorry. Yeah. What the annotator will have to do, they will have to go and manually, let's say, add points and fix the results that are here. And for this dog, and what happens in reality is that this annotation that is 91+% accurate is fairly good for any kind of application that you may have on your pipeline. Let's say you're trying to kind of swirl it, trying to, let's say, identify items in an object, in an image, and you have your user on their phone, they swipe, they put these points, and it crops out the background and does a reverse search. It would work very well, but one thing that it is not very good at is actual annotations. So once we are committed to having a data set that is perfectly annotated, and it is very important to have good annotations on your data set too. 91% for an annotation done by a human just doesn't cut it, and the annotator has to correct the things. So the most natural question to ask is, will this help? Will correcting a polygon be easier than drawing one from scratch? And the answer is it kind of depends. Let's try to annotate this wheel here, and again with 4 extreme points, kind of a box. A bit better than the dog, a bit worse than the dog, but in general, again, very good. Then you will have to kind of go here. Sorry, yeah, points are very small. Try to fix all these points. You can, of course, add points and so on. And research papers usually claim that their annotations are fast, that like this approach helps, and it reduces the annotation time by a significant amount, like 4 times. Some research papers claim, but they do not describe their methodology of how they actually compute these. And one thing you might notice is it really depends. The model is very sensitive to which points you choose. So let's try to annotate the dog, but this time let's choose different extreme points and see how it does. I don't know, let's say here, what is an extreme case? Here, I don't know, somewhere around here. And a bit worse, but in general, so this is very sensitive. When these research papers claim that with just 4 clicks, you can get 91% accuracy, they're correct, absolutely true, but it assumes the best positioning of this initial extreme points that you choose. And one more thing that to consider, which CurveGCN tried to resolve, is the annotation of blurred images, of blurred objects. Let's try to, I don't know, annotate this man over here and see how that works out. Not very well. Like these points have had to be a lot closer, and as you can see it. So I think that there is substantial research to be done on how much these methods reduce the annotation time. And like I said, this depends on how each person annotates, how well trained the model is, how well did it overfit, how well did it fit on the new data set, and the aptitude of the particular given annotator to choose correct points. But these were all real life problems when you try to implement the model and directly related to how the method works. But there are other issues here. The reason these predictions are very fast is because they use a GPU. On a CPU, it would be about twice as slower. So not terribly slow, like half a second for each prediction, but still. If you're an annotation platform and you're using instances that run, there are tons of issues connected with how much the network will be overloaded, how many users will be using this service, how many instances you have to sort of keep turned on a cloud server or cloud service of your choice, AWS, Azure, or anything else. And having a GPU instance running is usually quite pricey. And you have to factor in, if one decides to use these methods, one has to factor in those kind of issues as well. And another thing that you might notice when you're trying to annotate different types of objects is that it's really hard to get these 4 extreme points correctly, and you get these artifacts of straight lines where crops are done really bad. Well, there is a solution to this. You can actually just try to segment different things, right? Let's try, or let's just actually, sorry, let's just keep on this example. You can try to annotate parts of sorry, wrong tool. Something is gonna go back. Okay, you can try to annotate different parts. Let's say you think that you can find the extreme points of the leg and try to annotate the rest and then combine these polygons into one polygon, which is a fairly good approach. But then again, you run into some real life problems that your model has to be trained on things that look like a leg, and it might not work with 91% accuracy every time. So this kind of resolves the issue with not being able to annotate good extreme points for convex or very complex objects, but it introduces its own set. And another method that we can think about to reduce the costs and the runtime of the annotation process is to do the following. We can ask our annotators to annotate just 4 extreme points on every object that they find. Then once they're done annotating, we can run a batch job that would iterate over all images, find their polygons, draw them, and notify the annotation team that they can start fixing the polygon annotations. This method resolves every issue related with servers, with costs, but it makes it impossible to do it with the, or not impossible, but a bit hard to do the part annotation method, because you would have to annotate your point and then wait for some time for the entire process to finish and then start fixing it. But it's a fairly plausible approach. I find it to be a very good one. And our live coding session is related to this approach. And I will show you that how using our SDK and the pre-trained model that you may have, or you may use Dexter's provided method, or or your own method, or something from Hugging Face, how you can use these models to implement this approach using our platform, using our Python SDK. And yeah, live coding is always fun. Let's start. So let's jump into it. So we have a Jupyter notebook here, and we will need to import SuperAnnotate as SA, which is our SDK. I'm fairly sure we need to use JSONs. because our annotations are in JSON format. And okay, we will need to initialize our SDK. I have a config JSON right here, and what it has is it just has my token of my team, which I will redact after this presentation. And that's about it. It initializes, and now I can work with every image in my team. So let's have an image name here, and the image name will be, we can copy it from here. So we will try to, annotate it. Let's actually annotate the dog first. Put some extreme points here, and that's it. Okay, my computer is doing some weird stuff. Anyway, we have the image name, and we have a project name that I have called my project. What was it? Something like Coco subset. And this is our initial setup. What we need to do right now is we need to download image. And in order to download image, I guess you will need to specify the project, which is project. You will need to specify the image name, which is, in our case, image name. You will also need to download the image annotations. Then once again, project is project, image name. And if I remember correctly, I'm just looking at the documentation. This function has a local directory also as an input. So once we wait, while we wait for annotation and the image to download, I have here a model handler, which I wrote, and which is basically just the code provided by Dexter that this is the model that we're going to use. And let's just import our model handler from model handler. Why does it? Oh, sorry. It's the opposite. From model handler, import model handler. Makes much more sense. Let's initialize it. Let's have our model handler object. We will share the code with you. You will have it. It initialized our model handler. Or it didn't. What does it say? Oh, CUDA error. My CUDA is out of memory. So let's turn off some things and try again. Okay, now I have enough GPU memory to do this. Okay, so we at this point we have set up everything. We have our image, we have our annotations, which has one polygon. We have our model that will run the segmentation and find the rest of the points of the polygon. So let's have a function. Let's call it, I don't know, something like segment. That will get the image name. We will get the annotation name. Oh yeah, this is something specific to our platform. Once you download the annotation, it downloads them in with this name, basically the image name plus objects JSON. Let's say data is equal to none. Then with opening the annotation name in read form, that's file pointer data equals JSON.read load p, and we have our annotations. For instance in data instances, here we have the Polygon descriptions. You can actually see our format publicly on our docs.superannotate.com website if you're wondering how JSON is structured. And all we have to do here is we have to overwrite our points. We have our model handler, which has a function called handle prediction. It asks as a input a dict, which has an image name in it, which we do have, and point. And these are the extreme points that we annotate it, and the points are actually just itself. And that's it. This is the bulk of the work. Now we just have to save our new annotation file as fp sum.dump data and fp, pretty much it. So let's see if it works. Segment image name. No, because I had to write it in capital letters. Image name. What? It didn't download it. Let me see. It did download it. Why doesn't it? We have, this is the file, right? Do I have more than three?
I think you're missing an S after object.
Oh yeah, correct. Thank you. Object stitch. Again. And okay, yeah, it did. It ran our predictions. We had 2 instances, I don't know how. And all we have to do right now is we have to upload our image annotations. And again, looking at the documentation, we have to give it the project, the image name, and the annotation JSON file, which is basically just image name plus objects.json. And this is it. We're done. This is all it takes to automate the second method with our platform. Let's go and see if it worked. I hope it did. Didn't test it. It failed. Yeah, but it did found this thing. Oh yeah, okay, I know what happened. I did not save the annotation. It did find the person. We can try this again, but we will. Okay, so what happened is we annotated the dog, but we downloaded the annotation sooner than it was saved in our platform. Now let's just save it. Again, let me make sure that it is saved, and we can run the thing again. Let's download it. We have the new thing. We segment it again, and it makes more sense because we had just one dog, and upload it again. Cool. Another refresh. And yeah, it annotated the dog just like it did in the demo. So cool. This was pretty much everything that I wanted to talk about. So let's recap a bit. The annotation tools, the pros of the annotation tool is that it works as advertised. If you put the correct extreme point, it does a very good job at finding the instances. We don't actually know just how much it would reduce annotation time and for a particular annotator, but it depends on the tool as well. Like in our platform, I'm fairly sure you can fix it easily. Then, okay, another con is that the costs, and that you can solve it with this sort of batch annotation process, but that introduces its cons of having to wait for the annotation to complete, and you can't annotate a particular instance by part by part. But in general, yeah, this is the conclusion that we at SuperAnnotate got when we were researching various approaches, various tools to use for automatic instance segmentation in order to automate this process as much as possible. And if you have any questions, you can ask now if something was unclear or something you have other questions. Please stop sharing.
I think someone raised their hand, but
I don't see anything in the Q&A tab.
we got one. Why do you have to use 4 point? Can you start with 6 points?
The algorithm that we used was deep extreme cut, which uses 4 extreme points. As far as I am aware, there is no research that uses more points than 4. But the method that Dexter uses is that it basically crops the actual thing, the image with the instance using extreme points as bounding box. As a bounding box, it creates a heat map using these 4 extreme points. It concatenates them and uses this thing as one input sample. It is conceivable that you can use the same approach by having your training examples include 6 points or any number of points, actually, if you are willing to deal with recurrent networks, things that deal with arbitrary number of input sequences. That is also a possibility. The 4 points is just the limitation, or not actually the limitation, the feature of the deep extreme cut method, because the rationale was use as few points as possible to do things as quick as possible.
Great. We have another question asking if we're looking at a few interactive segmentation methods, what would be the best evaluation metrics?
Okay. So like I said, this is actually a very good question. The reason is that most research papers focus on the accuracy of the model that they have created, and it works as a good metric if you are trying to ship this model into production. But if you're trying to use the model as a tool for speeding up annotation time, I believe that the best metric for these methods would be to calculate the amount of time that an annotator saves while doing annotations completely manually or by using this approach. And in order to do that, it's a separate kind of a research problem. Then you will have to find a group of several annotators, give them the same images, decide upon different metrics, difficulty metrics. There's all sorts of stuff that is going to happen. You would have to calculate the bias that is introduced by the annotators. Some of them will learn how to use the model and pick the points better than others, all sorts of stuff. But at the end, for an annotation tool, the most important thing is how much does it reduce the annotation time while not compromising the quality.
Great. So what other semi-automatic segmentation methods are we supporting?
I don't think we're supporting any others, but what I showed in the live coding is that you can do any method. Like if like that other person asked to have some kind of a model that uses 6 points and does better job at it, you can have your model you can have your model and automate your annotations in that way. And we can actually support uploading your own model. I think that is something like that is work in somewhere in the roadmap of our tool. And we also, what we have right now is kind of a mechanism that allows you to listen to events, let's say annotating 100 images, and it will automatically run the code that we wrote together. You can write this code, you can listen to this, you can set up your pipeline so that once 100 images are annotated, this code will automatically run, and that kind of stuff.
Would these techniques work for semantic segmentation as well?
I believe so, because, well, yeah, I think so, because the only thing separating semantic segmentation from instance segmentation is that anything that has the same class in the semantic tasks is basically one big instance. So I do not see why you can't just annotate, put extreme points on every instance and assign them the same classes. Have your semantic pixel perfect mask reflect that design choice.
Great. And finally, how challenging would it be to try this technique out for videos?
Okay, let's think of it. If we're treating the video as just a sequence of independent frames, then not at all, because every frame is an image and we're basically done. However, the defining feature of a video is that it's continuous and every next frame depends on the previous one. And there are all sorts of interpolation methodologies that come into play that you would not want to annotate the same thing over and over. And if you're giving to different annotators to different frames that are very similar, again, they might choose different extreme points. So in technical terms, not very difficult. In practical, actual annotation time, fairly difficult. However, yeah, and also I don't have off the top of my head an example of a case where people tried to use both interpolation functionality in videos and something like box to polygon in conjunction with each other. And if you have errors in one algorithm and errors in the second algorithm and you use them in a chain, one right after the other, these errors tend to multiply. So I guess you would run into a lot of technical issues if you try to implement this for video. But another thing is that on video, I don't see very much research done on instance segmentation. Instead, a lot of focus is on object tracking, where you just draw a bounding box on the objects. So I don't know if it's actually feasible to even try to think about it at this point.
Awesome. All right. Well, thank you, Vahag, for the demo and for showing us the code. Thank you, everyone else, for the questions. I think that pretty much wraps up our session for today. Do join us again for our final session, where we'll be summing up what we've gone over the past couple of weeks and months. That'll be on June 23rd. We'll also be providing a recording of today's session, so be on the lookout for that as well. All right, thank you, everyone. Have a great day.